Good morning to one and all. Today we are going to discuss about the double linked list. Already in the previous videos we have seen the single linked list where every node will be having a link pointing to the next node of the linked list. Now we are going to see the double linked list, which is a complex type of linked list where each node contains a pointer to the previous node as well as the pointer to the next node. Therefore, in a double linked list, a node contains three parts. The first, as usual, the node data. Second one, the pointer to the next node in the sequence, that is the next pointer, and the pointer to the previous node, that is the previous pointer. So if you see the example for the structure of the double linked list, as an example, consider that the list contains data 1, 2, 3, 4, 5. So initially start is pointing to the first node, the first node is pointing to the second one, like that every node is pointing to the previous node and the next node. So that's why if you see in the structure of the double linked list, the node is consisting of three parts. The first part, as usual, it is the data, and the next part is a previous pointer which is pointing to the previous node, and the next pointer which is pointing to the next node in the double linked list. Start will always be pointing to the first node that we are having. In C programming, we represent the double linked list using this structure. The node is consisting of one self-referencing pointer called as previous, which is pointing to the previous node, and a data, whatever the data that we want to represent here, we will represent here, and a self-referential pointer called as next, which is pointing to the next node. Now if you see the representation of the double linked list in the memory, suppose consider that I am taking an example. The linked list is having the data hello, HELLO, 5 characters are there. We can represent these characters in the nodes, and these characters can be present in wherever that we want to store. We can store that in the memory. Suppose consider that HELLO has been stored like this. So initially start is pointing to the first memory location because start is pointing to the H. So the previous pointer, we don't have any previous node for this one. That's why I have represented into here. The meaning of the into is null. That's why we are representing the previous pointer is -1. And the next pointer is pointing to the E. E is present in third memory location. So we have represented 3 here. Now we are going to the E. So E, the previous node is H. H is present in first memory location. That's why here we are representing. L. L is present as a next pointer for this one. So that's why L is present in the sixth memory location. We are representing 6 here. Next node after the E is L. So the previous node of the L is E. That means it is present in third memory location. That's why previous pointer is pointing to the 3. And the next pointer is pointing to the another L that is present in the 7. And if you go for the second L that we are having, the previous node is L, which is present in 6th memory location, and the next node is O, which is present in the 9th memory location. And if you go for the O, the previous node for the O is L, which is present in the 7th memory location, and the next node is, it is null. That's why -1 we are representing. This is the way the double linked list is represented in the memory. And what are the advantages that we are having for the double linked list when compared to the single linked list? If you take the double linked list, it can be traversed in both forward direction and backward direction. That means if you want, you can go in the forward direction, or if you want in a backward direction also you can go. But in a single linked list, only in one direction you can go, either that is it is in the forward direction only. But if you take the circular linked list, we can go in forward direction and we can go in a backward direction, but we have to go to the first node once again. That is the disadvantage that we are having. The delete operation of the double linked list is efficient when compared to the single linked list operation, because every time when we are deleting a node in the single linked list, the previous node we are taking it as a pre-pointer, but in the double linked list there was no need of any pre-pointer. Similarly, we can quickly insert a node before a given node because there was no need of pre-pointer. So that's why these two operations, there is second advantage and third advantage, is related to the pre-pointer, that is pointing to the previous node that we are having. That is not at all needed here because the previous pointer is behaving as a pre-pointer for us. And if you see the operations on the double linked list, the first type of operations are inserting a node into the double linked list. There are already we have seen this in the single linked list. There are 4 types of insertions that we are having: inserting a node at the starting of the double linked list, inserting a node at the end, inserting a node before a given node, and inserting a node after a given node. We will see the 4 operations. The inserting a node at the starting. Suppose consider that this is the linked list that we are having, that is 10, 20, 30, and initially start is pointing to the 10. Now I want to insert 40 here. So 40 is the new node that we are creating and start is pointing to this one. Now I am establishing the 2 links here. What are the 2 links? New node of next is pointing to the start and start of previous is pointing to the new node. And after inserting this 40, the start is not the 10, the start is the 40. So what are the 3 things that we are performing? New node of next is equivalent to start and start of previous is equivalent to the new node and the new start is the new node. These are the 3 operations that we are performing when we are inserting a node at the starting of the double linked list. If we see the algorithm for this one, we are creating a new node initially. If node is not present, that is if double linked list is not present, start is presented null. At that time our new node will become as a start and we are closing this one. Otherwise, what are the 3 operations that we are performing? New node of next equal to start, start of previous is equivalent to new node and start is equivalent to new node. So if you see the function equivalent to this particular algorithm, initially we are creating the new node that we are using by using the getNode function we are creating. Whenever the start is equivalent to the null, that is there was no double linked list at all up to now. That's why our new node will become as the start. And for the sake of knowing the output, I am using the display function here and I am coming out of the function. Otherwise, that means already existing some linked list is there. In such case, what are the 3 operations that we are performing? The 3 operations are new node of next is equivalent to start and start of previous is equivalent to new node and start equal to new node. Those are the 3 operations that we are performing. At the end, we are displaying the output after inserting the node at the beginning of the double linked list. The next operation that we are having is inserting a node at the end of the double linked list. Suppose consider that this is the existing linked list that we are having. Now the start is pointing to the 1. Now I want to create a node at the end called as 9. So I am allocating the memory and I am initializing the data part with 9. That is I am creating a node here. Now 9 I have to insert after the 2. But I have to go to the ending of the linked list. For that particular purpose, like a single linked list, the pointer is starting at start. And when pointer of next not equivalent to null, I am going pointer to the next node. That is pointer equal to pointer of next. Like single node linked list traversing, we are traversing the double linked list. And the pointer we are reaching at this particular 2. So this is pointer and this is new node and we are attaching at the end by using the 2 links. I'll explain with another example this insertion at the end. See here 10, 20, 30 is there. Now I want to insert 40 which is pointing to the 300 memory location after insertion. See here previously it is into, that is null. Now pointer of next is pointing to the new node and the new node of previous is pointing to the pointer. So what are the 2 operations? Pointer of next is pointing to the new node and the new node of previous is pointing to the pointer. These are the 2 operations that we are performing for inserting a node at the end of the double linked list. If you see this particular thing, we are creating the new node. As usual, we are creating by using new node equal to get node. So I want to go to the end. That's why I am starting the pointer at start. That is here we are writing pointer equal to start. And I am repeating this particular step 3 until pointer of next is not equivalent to null. That is until the ending of the linked list. Pointer equal to pointer of next. That means I am reaching to the end. After reaching the end, what are the 2 operations that we are performing? Pointer of next equal to new node of previous equal to pointer. Those 2 steps we are writing here. So the same thing we have converted into the function. I am taking the new node and pointer. New node we are creating by using the get node function. Pointer we are starting at start, while pointer of next not equivalent to null. I am going up to the end by using the pointer equal to pointer of next. At the end, these two operations that we are performing, that is pointer of next equal to new node and the new node of previous equal to pointer. And the third operation is inserting a node after a given node. Suppose this is the example that we are having 17345. Now I want to insert this particular 9 after 3. I want to insert after 3, but I don't know where the 3 is present. That's why I am starting the pointer at 1. I am checking, is the pointer of data equal to 3? No, it is not equivalent to 3. So pointer equal to pointer of next. I am going to 7. Is the pointer of data equal to 3? No, it is 7. So pointer equal to pointer of next. Is pointer of data equal to 3? Yes, pointer of data is equivalent to 3. That means pointer is present at now 3. When it is pointer, this is pointer of next. I am inserting in the middle this particular 9. Okay, see here, this is the pointer, this is the pointer of next, and this is the new node. I am inserting between 3 and 4 this 9. That is after 3 I am inserting. This is the output that we are getting at the end. Now we will see with an example how this particular activity is happening after a particular node. See here, suppose I want to insert after the 10. I have searched for the 10 and I have reached the pointer here. This 10 is the pointer and this 20 is the pointer of next. Now I want to insert 40 in the middle. This is the new node. See here, every time when we are performing this particular operation, when the next node is present, at first we have to place the right first. That means new node of next equal to pointer of next of previous equal to new node. If this is the pointer of next, this link will be the pointer of next of previous. So that's why what are the two operations that we are performing? New node of next equal to pointer of next of previous equal to new node. Then these two links are established. Pointer of next equal to new node and the new node of previous equal to pointer. These are the four operations that we are performing. In the after case, always you have to perform right side first. See, this is the algorithm that we are having. We are creating the new node and we are reading the value and we are starting at the start and we are repeating the step 4 and step 5 while the pointer of data is not equivalent to value. That is, every time I am going from pointer equal to pointer of next. If pointer is equivalent to null, I am displaying that element can't be inserted. As an example, suppose consider that someone has asked me to insert after 50. 50 is not present. I have to tell that when the pointer is null, element cannot be inserted. Then these four operations what we have seen, we are performing at that particular point. This is the equivalent function that we are doing. We are creating a new node and I am asking to enter after what node we have to insert. Then pointer is starting at start, while pointer of data not equivalent to value, pointer equal to pointer of next. In the middle, if pointer is equivalent to null, I am displaying element not found. Then I am placing these four operations. Next, I want to insert a node before a given node. As an example, I want to insert 9 before 3. So I am checking pointer is starting here. Is 1 is equivalent to 3? No. I am going to 7. Is 7 is equivalent to 3? No. I am going to the next one. Is 3 is equivalent to 3? Yes, it is equivalent to 3. This is pointer. This is pointer of previous. I am inserting in the middle of this 7 and 3, this 9. That we will see with an example. Suppose consider that I want to insert before 20. So pointer is at 20 and this will become the pointer of previous. Now I want to place 40 in the middle. So when we are doing this one, at first perform the left side one, that is new node of previous equal to pointer of previous of next equal to new node, then the new node of next equal to pointer and the pointer of previous equal to new node. These are the four operations that I am performing here. See, at first we have to perform left hand side. This is the algorithm that we are having. We are reading the value. The pointer is starting at start, while the pointer of data is not equivalent to value, pointer equal to pointer of next. By using this one, I am reaching that particular thing. If pointer is equivalent to null, I am displaying element cannot be inserted. Then I am performing the four operations here, what we have seen. And this is the functional representation of this particular inserting the before.